All right, let's dive into something pretty incredible. We're going to unpack a groundbreaking study that maps out the literal electrical blueprint our brain follows to remember what we hear. And this isn't just some abstract idea, it's a peek under the hood at the high-speed data network running inside your head.
You know that feeling, right? Someone tells you their name, and poof, it's gone. You get directions, and they just evaporate. For a long time, we've kind of thought of memory as a switch. It's either on or it's off. But what if that whole picture has been wrong all along?
So to really get what's so new and exciting here, we first have to bust a really common myth about how memory is supposed to work.
Okay, so the old idea was pretty straightforward. You hear something, a part of your brain lights up like a light bulb. The brighter the bulb, the stronger the memory. Simple. But what this new research is showing is that it's not about isolated light bulbs at all. The real secret is in the wiring, the high-speed communication happening between them. It's a network, not just a bunch of hotspots.
So how in the world do you prove that? How do you stop just looking at which parts are lighting up and actually start listening in on the conversation they're having? Well, this is where the real detective work begins. I love this. The researchers themselves actually quoted Sherlock Holmes in their paper, and the point they're making is crystal clear. You can't just try to prove old ideas. You have to follow the evidence, wherever it leads. They were hunting for new clues. And their high-tech magnifying glass was something called QEEG. Now, you might have heard of fMRIs, which are great at showing which parts of the brain are active, kind of like seeing which computers in an office are powered on. But QEEG is different. It measures the brain's actual electrical chatter millisecond by millisecond. So you're not just seeing that the computers are on, you're listening to the actual data packets flying between them. And that's where the real story is. Which brings us to the big reveal. Using all that data, these scientists were able to map out the exact electrical patterns, the blueprint, really, for successfully remembering something you've just heard. So they mapped the whole journey, from the instant the sound hits your ears to how you recall it a few seconds later, and finally, the really complex dance the brain has to do to lock that memory in for good. Okay, look at this. This is the pattern for just listening successfully. And here's the first huge surprise. Listening is not a passive activity. For your brain to really grab onto information, a spot in your left temporal lobe, called T3, has to actively broadcast a synchronized alpha wave signal. You can think of these alpha waves as like the brain's pacemaker, getting a bunch of different regions to all pay attention in perfect rhythm. Now get this. When you need to remember that information just 30 seconds later, what does the brain do? It runs the exact same play. That same spot, T3, sends out the same signal to the same receivers. And this is so crucial. The quality of your memory is directly tied to how strong that first signal was. A weak broadcast going in means a fuzzy memory coming out. But to really cement that memory, to make it stick for the long haul, things get more advanced. A new player enters the game, the left frontal lobe, at a spot called F7. And it doesn't just listen anymore. It starts talking back, creating this dynamic two-way electrical conversation. It goes from a simple broadcast to a feedback loop. That is the signature of the brain locking in a memory. So, what is the big lesson here? What does this all add up to? Well, it gives us a brand new rule for how to think about the brain. It's a shift from looking at places to looking at pathways. If you take away one thing, let it be this. It's not about where the brain is active. What really truly matters is the synchronized communication, where that signal is coming from, and more importantly, where it's going. It's not about the towns, it's about the traffic on the highways connecting them. And this new blueprint? It doesn't just add to what we know, it completely flips some old theories on their head. It shows memory isn't just about activation levels. It totally contradicts a popular model that said the right frontal lobe was key for memory. Nope. This data says it's the left. And it proves that high synchronization isn't the brain idling. It's the very sign that information is being transferred successfully. Okay, so this is all fascinating science for sure. But here's where it gets personal. Here's where it gets really exciting. If we now know the blueprint for a great memory, can we actually use it? Can we rewire our own brains? Well, check this out. The study found a direct, measurable link in the data. People with higher education and better verbal skills consistently had stronger T3 projection patterns. That's that pacemaker signal we saw at the very beginning. The better your brain is at sending that first broadcast, the better your verbal memory tends to be. And that leads to a revolutionary question. I mean, if we know what the perfect electrical signature for memory looks like, could we actually train our brains to make it more often? Could we, practice making stronger memory signals, almost like lifting weights at the gym? The study gives us a jaw-dropping hint in its final lines.
They mentioned some preliminary follow-up work using neurotherapy based on these exact principles. And the results? The subjects improved their ability to recall paragraphs by, get this, between 33 and 187%. I mean, that's not a small improvement. That is a life-changing leap.
So that leaves us with this incredible thought to chew on. We're moving beyond just observing the brain to actually understanding its operating system. So, what happens when we can not only read the blueprint for a perfect memory, but actively help our brains build it? Just imagine the possibilities.